Usually David's running all over the place. So
Yeah.
I can tell him when he comes up with it.
I think we're good, so we can start whenever
Okay.
you're ready.
Great. All right. So I'd like to introduce our speaker today, Suman Jumani, who is an applied scientist with the global, I can't read, project and durable freshwater protection teams at the Nature Conservancy. She completed her ORISE, which, if you don't know, that's Oak Ridge Institute of Science and Education fellowship with the U.S. Army Corps of Engineers and Network for Engineering with Nature. And her PhD from the University of Florida. So actually, she worked with Matt out in the Panhandle, but spent most of her time here on campus. Her work is centered around freshwater systems and spans a range of topics, including dam removals, nature-based solutions, biodiversity accounting, and conservation science and planning. So with that, Suman, you have the floor or the screen in this case.
Thank you. So very happy to be here, and particularly in this room, although it's virtually. So when I did my PhD at UF, Dr. Kaplan was kind of my in-house advisor on campus, so I landed up attending a lot of lab meetings and seminars right there. It's great to be back. So today we're going to talk about all things dam removal. And before I get started, I just want to say that the work I'm going to be presenting today has been something we've developed collaboratively across several agencies and institutions. And several bits of this work have been, shaped, led, co-authored by all these wonderful people listed here. And my capacity in this whole thing was a postdoctoral researcher with the Army Corps of Engineers and the Network for Engineering with Nature. I know that the University of Florida is also a partner with NUN, so several of y'all in the room may be aware of NUN or maybe even part of NUN projects, which is amazing. And today we're just going to talk about the context of dam removals in general with the focus on the US. And then discuss these three little resources our team has kind of put together over the past 1.5 years. So starting off with dams in the United States. So the US has been building dams for a long, long time. History of dam development goes way back. And a consequence of that is that several dams today are really old. And while that's not inherently a bad thing, what that means is that a lot of the older dams may not be up to current code, and they may not be suited to work under current climate regimes, hydrologic regimes, and current forms of land use. And also because they're very old and, through the processes of sedimentation, lack of maintenance over time, many of these dams also start approaching the end of their reservoir design life, around 50 to 100 years. And so today, the National Register of Large Dams in the US, which is called the NID, the National Inventory of Dams, the average age of a dam in the NID is over 60 years old. And a lot of these dams are in poor physical condition, so they may not be capable of withholding normal to slightly above normal loading conditions. And them being in poor structural condition is just one part of the story. In addition to condition, you have something called the hazard rating, and that basically indicates what the consequences of that particular dam failing or breaching will be. And within the NID, about 17% of the dams are high hazard. And what that really means is that in the event of one of these dams failing, the likelihood of loss of human life is pretty high. The ASDSO estimates that about $66 billion will be required to rehabilitate all of these non-federal aging dams. And because of all of this, the most recent ASCE infrastructure report card rated dams, they give them a grade of D, which is kind of like amongst the lowest grade of any infrastructure category in the US. And given that these dams are aging and lots of them are in poor condition and pose high hazard, there is, of course, a growing concern about the safety risks that these dams pose. So there've been several cases of dams coming close to failing or actually even completely breaching. As you can see here, the case of the Edenville and Sanford dams in Michigan, which were about 90 years old. They breached in 2020. Both of these were high hazard dams. Similarly, the Bastrop Dam, which was over 100 years old in Texas, that breached. And all of these breachings tended to happen during extreme rainfall events, particularly showcasing how these aging dams are not really able to withstand today's changing climate. Another consequence of this is a lot of these old dams, the mill dams that we were just discussing earlier, or these mine tailing dams, are kind of obsolete. So this particular news article here that you're looking at with the EPA pertain to pertain to a mine that closed in 1923. So that particular dam holding those toxic, or contaminated soils behind the reservoir, including arsenic and heavy metals, has just been sitting around since the 1920s, and probably due to lack of maintenance, non-active use, when the EPA tried to deal with that dam, it resulted in toxic waste spreading down the river network. So the problem, unfortunately, with the NID is just one small part, because the National Inventory of Dams captures or has only about 91 to 92,000 dams that meet certain height and storage criteria. But it's estimated that about 2 million impoundments in the United States are not really captured in the NID. So what we know from the NID is just part of the problem. The scope of the problem is actually much larger. And one might think that, okay, there are these small dams. Okay, are they even really a big part of the problem? And turns out they are, because the little statistics we have do kind of indicate that it can be massive. So for instance, in just South Carolina, the state incurred costs of about $7 million to repair roads from breach of these unregulated dams in just 1 year. And shifting gears, we all know dams cause massive environmental havoc. They impede connectivity, the free flow of water, sediment, biota through river networks. And so removing some of these structures holds huge potential to mitigate environmental impacts. And we all must have seen these kinds of infographics that talk about the scope to unlock upstream river miles, restore fish passages through dam removal. And I guess all of this to say that all these different causes have kind of come together and created the perfect breeding grounds to promote more and more dam removals today and going forward. Sorry. So as of 2021, in the US, over 2,000 dams have been removed, which is amazing. And you can see through this time chart here that the rate and pace of dam removals have really picked up in the last 2 decades, and it's expected to continue to rise. We also see that the removals have not been equally distributed. They are largely concentrated in Pennsylvania, California, Wisconsin. And there are reasons for that, state-based reasons in terms of stricter enforcement of dam regulations, streamlined permitting, policies, etc. And where are we going forward? So we know that there are lots of compelling reasons to bring down certain dams. We're also in an enabling policy and funding window. There's more and more money and policies being created to facilitate or enable these removals to actually happen. And it's estimated that by 2050, there will be over 35,000 more dams being pulled down. So given that we're at this stage, one can appreciate that there's immense scope for a more strategic approach to dam removal planning, because the 2,000 dams I showed you before, most of them to date have been removed in an opportunistic one-off way, where it's reactive, where the dam's in really bad condition, it's posing a huge danger, and so people go and try to take it out, or it's local NGOs, community groups, working with then local knowledge to remove dams they know inherently are bad, but there's no real strategic approach to deciding which dams we want to remove and retain. And what makes it complicated is, there are many actors in the dam removal space, many people who support dam removals and those who oppose it. And that's one of the challenges towards strategic decision making. So, for instance, the dam owner may care about maintaining the dam and minimizing their long-term costs or making good money off it. They want to be profitable. The dam safety officials from the state and the federal levels would care about protecting the public from any safety or hazard that the dam poses. Similarly, the environmental regulator or conservationists like us, folks from, who care about the environment, may want to mitigate the environmental impacts of dams and particularly focus on migratory, threatened, and endangered species. The Department of Transportation is also a player because they care about maintaining road networks for dams, and in some cases, dams constitute important components of the terrestrial navigation system. The river recreator, water-based recreation activities are big in the US, and they are an important stakeholder. Lots of people like to hold on to some of these dams as they associate these structures as a historical structure that, speaks to their sense of place or sense of identity. Local infrastructure planners are a big player because, if you're bringing down a dam and that brings down the water level, that affects, say, water intakes systems in place and affects the city's water supply. That's something that's not going to fly. So you have to rope in them as well. And a relatively new player in this space is the mitigation banker. So with the Army Corps, there are now recent policies that allow one to remove dams and earn compensatory credits, mitigation credits that can then be used towards other projects. So as you can see, each of these players bring their different objectives and values and constraints to the decision that one has to make. And so, structured decision making is a great tool to use within these contexts. There are many structured decision frameworks, the most common of which is this PROACT framework, and that stands for the different steps that goes within this whole process. So we start off by defining the problem. Are we looking at different alternatives for a single dam, or are we looking at assessing a portfolio of dams and find the best one for removal? What are our objectives and metrics that we care about? What are the potential alternatives we could consider, and how do you estimate the consequences and trade-offs between them? And then you come up with your decision. So such a process is particularly suited to the dam removal context because these are usually publicly funded decisions. There are lots of people involved, and it gives us a transparent way to go through the entire process. Although it does, certain challenges continue to remain, such as who sets the objectives, what do we want to consider, how many metrics to include, how do we assess trade-offs, the list goes on and on. So our team, we put together this 3 little resources to kind of help with dam removal planning in the applied space. And these tools could be applied together, in tandem, in isolation, and through different phases of the dam removal project. So let's dive right into them. The first tool is the objective and metric selector tool. This was created by Laura Naslund, who's a PhD student at the University of Georgia. And her work started off with a literature review. So she looked at existing tools that aimed to either prioritize dam removals or dam placement. She looked at both removals and placement, and particularly focused on tools that comprised of 2 or more objectives. So if you were just a tool looking at maximizing your upstream miles, that did not qualify. A total of 41 tools were identified, and these were a list of common objectives that we found in the literature. So we don't have to go through the entire list, but these can be kind of categorized into 5 main categories, which are outlined in blue. And so not surprisingly, they include things like accounting for monetary costs and feasibility, meeting the demands of the infrastructure. So what the purpose of the dam was it power generation, water supply, making sure that function remains, reducing potential safety hazards to downstream communities and property, meeting community desires for recreation or historic preservation, sense of place, and then finally restoring the biological integrity of the nation's waters, right? Physical, chemical, biological. And the different actors we spoke about, one can start linking these different actors to the different objectives, right? Although a single actor can be concerned with more than one objective, we know that there are particular objectives that some actors would be more concerned with relative to others. In looking at the prevalence of these different objectives in the literature, we see that, not surprisingly, focus on focal taxa benefiting from dam removals and implementation cost were the most prevalent of the lot. However, most tools, like almost 75% of all the tools, included just one or two objectives in dam removal planning, which is extremely limiting. None of the tools included the objective of reduction in stream geomorphic degradation. And what I mean by that is, like, when you have a dam that's holding back sediment, you can have undercutting and bank destabilization, which can then affect infrastructure. And removing the dam potentially reestablishes that connectivity and avoiding that problem. So that was something that wasn't really considered as a service or disservice. And the most commonly co-occurring objectives were focal taxa and cost, and focal taxa and meeting power demands. So to kind of make all of these objectives accessible and to promote their inclusion in future projects, what Laura did is she developed a web application, a Shiny web app, where we listed out all of these objectives. Each objective was then also linked with different metrics one could use to quantify those objectives. And for each metric, we had a method on how one would go about quantifying. So for instance, if we cared about improving upstream connectivity, a metric could be longitudinal connectivity. And the ways to measure it could be looking at an index of longitudinal connectivity, looking at upstream miles, the longest length of free-flowing river. And for each of these, we have this more information button. And yeah, so this is QR code that will take you to the Shiny web app. And I can maybe show you a very quick demo right away. Can you see my screen?
Yes.
Okay, just give me a second while this loads. And if it takes too long, we can move ahead. There we go. So the dam metric selector. So the homepage has a whole bunch of information. This is currently under review, which is why it says draft. The objectives are here, the 5 categories and the list. So if you're a person removing a dam, you could sit with your stakeholders, select the objectives that matter to you, and you can select several, hit next. And then for the selected objectives, you get a bunch of metrics, methods. You have more information to linking to data sets, citations, studies that have used these methods, and you can download this to use on the go, right? And we're back. So that's one of the tools we've put out there. The next is the decision support framework. So we have all of these objectives, we have all of this information. How do we bring it all together to actually facilitate an actual decision? Just excuse. Yeah. So we know there are different types of, when we think about dam removal decisions, they could happen through different ways. So one is the more reactive and informal that we spoke about, where you have an unexpected failure, you're reacting to a strong situation, or you're using local knowledge, which is still fantastic. I mean, I think that's really what's driven the existing dam removal so far. But towards the more proactive and formal side of things, you can have these scoring and ranking methods to pick amongst portfolio of dams. You could have GIS-based optimizations or a mathematical optimization where you're looking for the best combination of dams to maximize a parameter or minimize another constraint. And not surprisingly, the complexity and spatial scale of prioritization increases as you move down towards the right, and your uncertainty reduces. However, in talking to actual practitioners on the ground, like folks from American Rivers, TNC, other NGOs who are working within this space, We find that, I mean, what they say is that there are a lot of constraints in terms of using what exists in the literature, because most tools operate within single or related disciplines. So you might look at upstream river miles and anadromous species, or upstream river miles and connectivity. So you're just looking at the ecology, and that's kind of not capturing the whole picture, as in it doesn't consider the range of economic, social, and ecological factors, right? And in terms of optimization, the high computational rigor often impedes its use by any, a practitioner on the ground. And with these optimization tools, you can usually optimize for a handful of factors, like 2, 3, maybe 5 if you're feeling a bit crazy. But if you really want to encompass a whole range of considerations, it gets really difficult. So in discussing with these folks, we kind of asked them what would be interesting character, what would be desirable in a prioritization tool, as characteristics that you all would like to see and use. And these are the features we saw. People wanted tools that could incorporate multidisciplinary criteria, stakeholder values, work within existing data availability. They wanted it to be something that's computationally accessible, that they can see and fully understand what's going on, and that the results should be easy to communicate. And coming from the background of Noon, we also wanted our tool to be one that doesn't necessarily identify the best option or give you a deterministic rank, but put together a tool that can identify dams that can provide multiple types of co-benefits. So dams that are economically and opportunistically feasible, ecologically beneficial, and socially acceptable. And so we decided to use a multi-criteria decision analysis framework. And we kind of condensed all those different objectives and criteria into 3 tiers, or 3 dimensions, if you will. So the first tier looks at opportunistic considerations, right? Is this dam really old? Is it no longer providing its intended function, working at very low efficiency? Is it at risk of failure? Or is it costing a lot of money to maintain such that it may be economically more viable to remove? We also looked at the ecological considerations, restoring connectivity, flows, improving fish passage, overall riverine resilience. And then finally, the social considerations. A lot of indigenous communities hold, free-flowing rivers and migratory species as culturally and traditionally, important and something that they revere. So removing dams for those reasons we are starting to see a rise in them. In fact, that played a big role in the Climate Dam Removal Agreement. Dams could be removed for safety reasons, for recreational reasons, and they could also have an economic impact. For instance, a lot of folks oppose dam removals because they feel it could lower their property values once a dam has been removed and you no longer have that permanent waterfront. And some folks feel otherwise. So there are all these services and disservices to kind of consider across these 3 tiers or dimensions. And for each tier, we kind of had this goal, right? So within tier 1, the variables or the decision criteria one would consider would be those that maximize this goal, which is you'd consider variables that could help you identify dams whose removal would be opportunistically viable. It would improve safety, and it would minimize the loss of critical services. So we wouldn't want to remove a big dam that's providing water supply, flood control, and hydropower benefits to, say, in the California Valley, right? Goal 2, the variables selected in this tier should be those that help us identify dams whose removal can result in improvements to, riverine ecosystem integrity, biodiversity, and function. And finally, goal 3, and we can ignore the rest of this graphic, but just focus on the tier 3. And goal 3 could be those that help us identify dam removals that would be beneficial or acceptable to the local community. And this is kind of important because several dam removal projects that seem great in terms of goal 1 and goal 2 really get caught up or tangled up in goal 3, and people spend years and lose a lot of money and time in litigation due to contentious feelings of communities and stakeholder groups on ground. So in our application of the framework under this tier, these were the 5 variables we selected. But one could use the objective selector tool and pick the variables that make sense to their particular use case scenario and decision context, keeping in mind that we want only variables that fit the criteria of this goal. And one important thing is, since we're considering all these different variables, these variables are measured using different units at different scales. So there is this thing of combining all these different types of data. And so the MCDA framework allows you to do just that. You can scale all your variables to a single unified scale. Each of these variables can be assigned stakeholder-informed weights, which implies how important each criteria is. Different groups do this differently. You could have a workshop where stakeholders come together and iteratively decide on what weights are. You could have different stakeholders sit in different rooms and run their own do their own prioritization through this framework using their own weights, and then you come and try and reconcile results. And then we use a weighted sum model to kind of combine all of this together such that every dam is then scored between 0 and 1, where 0 implies it doesn't do well in terms of opportunistic feasibility, and 1 implies that it's a good candidate for removal. Similarly with tier 2, as you can see here in our use case, in our application, we included 10 variables, 5 of them hydrologic and 5 of them ecological, and you can get these similar outputs. And what the outputs from both of these would result in this removal suitability biplot is what we call it. So the relative positions of dams against each other within this biplot indicate their gradient of removal suitability. We don't like to particularly give them ranks or be too discrete about it, because there is always uncertainty in the data you selected. There's some sensitivity in the method you use. So generally, the options up here are good and these are bad. However, for the sake of communication, if we were to split this into 4 discrete quadrants, we would get something like this, where dams that fall up here would be a good priority for removal since they're opportunistically feasible and ecologically beneficial to remove. However, dams that fall here are probably dams that are still functioning well or providing a critical service, but their removal would be ecologically really beneficial. So those dams may be good to restore, maybe through a fish ladder or improved flow, flow regulation, if not remove. The dams down here, which are ecologically suboptimal, we wouldn't want to remove them for ecological benefit, but we may want to remove them for safety reasons, or if we're removing a combination of dams and this pops up as important. And again, the poor candidates are one we wouldn't want to waste our precious resources removing. And you can see these mapped out spatially as well. And once we get this, the shortlisted bunch of good candidates can be subject to a tier 3 assessment, which is sociocultural considerations. And since that's super context dependent and site specific, the best way to get at that is through community engagement, identifying the stakeholders on ground, discussing or communicating the risks and benefits of the dam removal with them, responding to their concerns. And this is a really long drawn process, which will take time and could change also over time, right? However, if you're assessing a bunch of dams and thinking about removing more than 1, 2, 3, 4 dams in a basin, we might also wish to do a spatial optimization to account for spatial dependencies. Because if we go with naive scores, we might just get at inefficient solutions. But again, in our experience, most practitioners are operating 1 dam at a time. It would be amazing the day we get to planning several at a go. And we applied this as a proof of concept to the North Coast region in California. And this included 6 of these small little coastal rivers. And all in all, the 25 dams that we considered for removal after some filtering criteria to exclude the really young dams and dams that had very low chance of removing, we got this kind of a biplot. We were able to identify 4 dams that would be of high priority to remove based on their tier 1 on tier 2 scores, so the opportunity and hydroecological scores. We also looked at the cost, what the expected cost of removing these dams would be. And that could be a variable of interest, something that could influence your decision, but we didn't weigh it in as a decision criteria. And what's cool about this is you can kind of unpack what's going on behind those scores, right? So for those 4 dams, we try to see what's really driving it. So tier 1 was being driven by a loss of function, and tier 2 was being driven by anadromous species and freshwater biodiversity. So these kind of checks make sense because you don't want to, be swept away by the numbers. And if this looks not right, or you don't want your function to have such a strong influence on the final outcome, one could go back and tweak those weights. So it's an iterative process. And given that those 4 dams were identified as important, now an in-depth socio-cultural tier 3 assessment was beyond the scope of our study, which was just a proof of concept. So we relied on site-specific qualitative expertise to get like a first level approximation of what tier 3 may be. So we looked at community attachment to the dam, loss of critical function, and expected cultural or traditional benefits from removal. Were they indigenous groups who had a stake and who were lobbying for the removal of any of these dams? And what we found is that 2 of these dams had a very, very, very low chance of removal just because they played such a big role in the community in terms of day-to-day use and recreation, and they provided lots of critical function. However, the other 2 turned out to hold good potential. So again, this is just a proof of concept. And what this framework does is it helps you identify pools of dam removal options that can align and generate different types of benefit. So you're kind of improving the viability of your project. You can start tapping into different sources of funding. You can get stakeholder buy-in. What this tool is not is an optimization tool. It does not do optimization. And since the input decision criteria and the weights really drive the output, it's really important to recognize that the outputs of this tool are completely value-driven, and the people using it need to have that awareness and expertise of the region. And again, we envision this being used as just a first level of prioritization to get to that level of a more proactive approach to dam removal. And final, cost estimation. How much time do I have?
About 10 minutes.
Okay, perfect. That's perfect. Money drives everything, right? You go into Rome, you talk about a dam removal, and the first question is, how much is it going to cost us? So it influences your project viability. It's a big constraint when it comes to prioritization. And more importantly, accounting for costs within the cost-benefit analysis, the life cycle cost of these projects becomes really important. And we currently do not consider decommissioning costs when we are doing the cost-benefit analysis of new infrastructure projects. So having some cost estimates at hand is very, very important and useful. Jeffrey Duda from the USGS and his colleagues put together one of the first databases of dam removal costs in the US. It includes about 668 dams. And since they were removed across different periods of time, the costs were adjusted to 2020 US dollar values. The data set includes dam attributes like height and material, site attributes like state, what's the discharge, the drainage area, and also these complexity drivers. So these were 28 variables, which would add complexity to a given dam removal project. And for every project, those drivers were either present or no. So it was a binary variable, right? So for instance, under the sediment management drivers, we had variables like contaminated sediment, manual removal required, building a cofferdam, dredging. So those were either ones or zeros. And the more ones they are, the more complex the project is in terms of the actual engineering of removing it. So we built a model to predict cost, and we split this data set into an 80% training data set on which we built the model, and a 20% testing data on which we applied and tested the performance of the model. The model was built using this machine learning technique called the stochastic gradient boosting method. And basically what that does is it builds several sequential shallow regression trees such that each tree improves upon the previous tree. So it improves upon the residues of the previous tree, and you build thousands of them. And we also incorporated different quantiles to get at a predicted point estimate, but then also a 50% and a 90% prediction interval. We assessed our model using the R-squared and mean absolute error. And yeah, this is just the summary of the input predictive variables. So we had things like dam height, dam material, and project complexity, which was a 0 to 1 score from those 28 binary complexity drivers. And site attributes, like what was the discharge at the dam site, what was the drainage area, and what state or region did the dam fall in. And not surprisingly, we saw that dam height, discharge, and project complexity were the strongest drivers of removal cost. And this model explained about 57% of the variance we saw in costs. Of course, things like drainage area, the region, the material durability, that the dam was built with, all of these influence cost as well. And southwest, the dam removals were more expensive, and the northeast, they were much cheaper. And when we applied this model to the test data and we looked at the actual and predicted cost values, the R-square was about 44%, which is not great, but not awful either. And the mean absolute error was about $1.5 million. Again, standardized to 2020 values. And what we saw here is for dams that cost, that were on the lower end of removal in terms of cost, our model tended to overpredict the cost. And for dams that cost a lot to remove, our model tended to underestimate the cost a little bit. The extent of error was also larger for the very large dams, and that's because their representation and the inherent cost database was limited. Most of the dams removed so far have been small, and that's where our confidence is the best. Having said that, these 50% and 95% prediction intervals almost always encompass the actual cost. So the way we encourage people to use this tool is to look at, the point cost estimates, but to also very seriously consider the entire range of the 50% and 95% prediction interval. And again, to make this tool accessible, we put together a Shiny tool so that anyone could actually go in and feed in your dam details and get a cost estimate. And again, we can just go in and look at this tool. The first time you load it, it takes a minute, but once it's connected, it kind of works a lot quicker. So this is the dam removal cost estimator tool. You can have, there's your introduction, and your second tab is the cost prediction. So you can feed in your dam height. Here it's in meters. You can make that 20 meters. You can change your dam material. And since complexity is a score, one would have to estimate, right? We've given folks an anchor value because the Elwha dams had a complexity of 0.98. That was one of the most complex dam removals. So you could take a range of complexity values. You can estimate that for your dam, it may be 0.6 to 0.9. And you get these cost estimates with your prediction intervals. For the hydrology inputs, you can either put in the COM ID of the NHD reach on which the dam is located, or you can input your actual discharge and drainage area. And the different tabs give you descriptions of the model. We have one case study that talks about a case where our actual and predicted costs aligned really well together, and one where they did not. The actual and predicted were far apart, and why that was. And so this tool really looks at the engineering value of the actual removal and doesn't really look at added costs due to prolonged timeline from litigation, social issues, having to do EIA studies, all of that. So those are really not captured within this model. And we have actually developed a version 2 of this model, which does away with the need to predict that complexity parameter. We've instead relied on geospatial proxy variables. And what that allows us to do is estimate cost of removing every dam within the US, for which we have basic input values. And this paper is kind of ongoing, where we are looking at the monetary investments required to manage this problem of aging dams at a national scale. So we are looking at different scenarios, like what's the total cost of removing all dams that are above 75 years old and pose, a high hazard and are in poor condition. So we're looking at all these different scenarios, looking at age, condition, hazard, also biodiversity. And that's something that's very interesting and I'm excited about. If any of y'all are going to the World Fisheries Congress, we'll be presenting that work there. So yeah, that's a quick recap of the work we've been doing in this space. And as final takeaways, coming back to that number of 66 billion required to rehabilitate these non-federal dams, our numbers are slightly lower, but we're only looking at removal and of dams that meet certain thresholds. Having said that, the scope of the problem is huge. The recent bipartisan infrastructure law, or the IIJA, takes a $3 billion bite out of this required amount. But needless to say, it's not nearly enough. Given that, the scope of the problem is really large, the resources we have are not nearly adequate. Pushing for a more proactive approach to managing this problem becomes really important. And we hope through this work that we've added some tools out there that can help people achieve that. So with that, I will stop and open it up for questions.
Thank you, Suman. So, I think we'll start online since all of you seem to require extra time. So does anybody online have a question for Suman? Okay, does anybody in the room have a question? Excellent, we have a question.
It's not a super interesting question, but I think it was on the graph for cost removal where you were comparing the predicted cost to the actual cost of the dam. I was curious what the gray bars represent in that diagram.
Yes, I should have been clearer about that. So these gray bars are the prediction intervals around the cost. The dark gray line indicates the 50% prediction interval, and the light gray looks at the 95% prediction. So what we were trying to do is estimate the cost of removal, but our input data was just 668 dams, of which we used only 80% to build our model. Also, the input data has information on mostly small dams. And so we felt it was only responsible that our model not just give us point estimates of cost, but actually gives us a prediction range. So the 50% prediction range and the 95% prediction range is something we suggest users, kind of consider as a conservative suggestion given the limitations of the input data.
Thank you.
Other questions? I've got one, Suman. You mentioned that the likelihood of future climate change creating uncertainty with regards to or intensification of rainfall events heightens the desire to remove those high-risk dams. But I guess it's not in I don't think it's in your model, but do you hear people actually wanting to keep dams specifically because of the uncertainties of future rainfall and actually trying to manage that water in a mechanical way instead of letting Mother Nature choose?
Yeah, so that's something that's really cool, and it's hard to know what's going to happen where. We haven't really considered it in our model, but in talking to people, we do see that some dams are flagged as extremely important given changes in climate and precipitation as water storage structures, and they're often augmented with secondary water storage structures. Like there's this whole focus on augmenting gray infrastructure with green infrastructure. So dams as water storage in their reservoir, but then also doubling up on groundwater storage to deal with these extreme rainfall events. So yeah, we are hearing those conversations. I haven't seen cases of them being completely realized and spatially mapped out.
Last chance, otherwise I gotta know. So second question, you mentioned that there was about $3 billion in the infrastructure bill that's going to help support or move towards that 66 billion. But how is a typical, or those dams that have been removed, where does the general funding for those come from? Is that a compilation of what the primary driver is in the sense of, is it high risk and therefore transportation pays, or if it's desirable for fish and wildlife habitat or some endangered species that's coming out of, say, federal U.S. Fish and Wildlife dollars or something? Where does the general money come from for those projects?
Yeah, you guess absolutely right. Depending on how you frame the project, you can actually tap into different pools of money. So if it's a safety issue, you can tap into state and federal pools set aside for that. There's a lot of money now being available through Fish and Wildlife and the National Marine Fishery. There's lots of acronyms in the US, and I'm still learning all of them. But they have big funds set aside for dam removal. And that's one of the biggest advantages we see about using this, the kind of, the framework that we proposed for prioritization, where you're not getting at the most optimal best. You're getting these pools of options that offer win-win-win across different dimensions. So you can really then be creative about then getting the kind of funding you need for that dam removal. So if it's a dam that's meeting safety issues and ecological issues and social issues, the kind of funding sources you can apply to suddenly increase many-fold, thereby increasing the chances of that project getting funded. And on that front, there are a whole bunch of manuals that are being put out by the federal government on guidances on where one can seek funding for their projects based on location, objectives, scope of the project, folks benefiting. So, yeah, a lot to consider there.
Okay, thank you. Last chance.
I have
All right.
a quick question.
Go ahead, Alyssa.
So I'm interested in, are there cases where modeling such as this and the assessment phase leads to funding? And in which case, like, what kind of examples are there for, large infrastructure like this? Because it is a lot of money to get funding for, and I'm just wondering if this was kind of rooted in a similar circumstance that you saw that inspired this conceptualization of the problems. Thank you.
Yeah, that's a great question. And I'm going to say I don't entirely know the answer to that. Our work was motivated to kind of enable more dam removals happening at local to regional scales. But, in terms of even considering the infrastructure bill that came out, it's very likely that the ASDSO estimates of 66 billion and the lobbying by several groups and, talking about the scale of this problem is what eventually led them to budget that significant amount towards dam removal. And so we hope, especially the work that's underway, which we're talking about, the national assessment of monetary investments needed. We hope that would be amazing if it could be leveraged to kind of make more money or make more resources available to address the problem.
All right, last round of applause for Suman.
Thank you.
Thank you, Suman. Great work. Nice presentation.
Thank you so much. Happy lunch. Bye.
Thanks, everybody. Don't touch anything.